All right, our last video for derivatives that we're going to look at is when if we find derivatives using power, product, chain, implicit, whatever we've done up till now, is what happens if we have a derivative. Could we take another derivative? So if we took that answer and did the derivative again, and then could we take that answer and do the derivative again? So the answer is yes, we can do higher orders. We can do first, second, third, fourth, fifth derivatives. It really doesn't matter. The issue is why would we want to do them, or what does that help us do? We're not going to worry about that so much today. I'll explain a little bit of the method behind it, but we're just going to worry about how to do it today, figure out how it works and get that part figured out, and then we'll figure out the why in a later unit. So in terms of notation, we can either use the prime notation. So you can see on this title page, I've got using primes. So we got like prime 1, prime 2, or 3. And the same thing if it was y, 1, 2, 3. We don't typically go to a fourth derivative, but if you do, instead of writing it as y with like 4 ticks, I've seen it that way. Some people do like Roman numerals, which is fine. Or we just put 4 in a bracket just so that it doesn't look like y to the power of 4. But it doesn't happen very often anyway. And then the other version using dy dx, you can see the first derivative would be dy dx, the second has a squared, the third would be cubed, fourth would be to the power of 4, and so on. Some people often wonder why is the squared in the middle and then the cubed on the end, on the bottom and stuff. We'll talk about that in a second. So with higher orders, we basically find the derivative of the derivative. So we call that the second derivative. And if we took that answer, did it again, we'd get third derivative, and so on. So we've already talked a little about the notation. So the reason why the second notation is weird, most people understand the prime. If y prime is the first derivative, y double prime would be the second, and so on. So in order to get the notation, let's clarify that a little bit. So if I gave you an equation like y equals x to the 6th, our first derivative would be 6x to the 5, doing power rule. So now what we're doing is we want to do the derivative of that. So you can see in terms of the equation, we basically do the derivative of the derivative, but really the y doesn't ever change. We're never changing the y equals x to the 6th. So all we're kind of doing really is just doing another d over dx. Oops, let me fix that a little bit. Maybe let me erase this whole thing and I'll kind of fix that a little bit better right from the start. Okay, let's see, my eraser doesn't seem to be working here. Let's try it one more time. No. Okay, so let me kind of erase this here. And let's start again. So if I gave you the derivative, let me write y equals x to the 6th. So our first derivatives, we're saying let's do the derivative with respect to x of y. So that's what we got, 6x to the 5. So now our second derivative is let's doing the derivative of that derivative. Right? We're not changing the y, we're just basically doing another d over dx. And that would give us 30x to the 4th, so that's pretty easy. But you can see the notation, we kind of have 2 d's on the top, so that's why we write it as d squared. And then we have 2 dx's on the bottom, which would be written as dx squared, and then the y doesn't change. So the y in the equation really doesn't change, it's just all the d's and the dx's that changes. So that's kind of why the notation looks a little bit weird. But after that, we'd be able to keep on going. So our third derivative would be d cubed y over dx cubed. And we do it again, so bring the 4 down, 4 times 30 would be 120, x to the 3. So how to do the second derivatives and third derivatives are usually quite simple. So here's another example, let's try it again. So first derivative of this one, it's just power rule for each term, so we'd have 3x cubed. Power rule again would give us 4x, and then 5. Our next derivative, take that answer, do it again, we'd get 9x squared minus 4. Last derivative, do the same thing, we'd have 18x. So you can see power rule works pretty good. The chain rule works almost as good. Let's just do a quick chain rule example. So if I gave you something like 2x plus 3 to the power of 4, if we did our first derivative, we would bring the 4 down, drop it to a 3, but we'd have to times by 2 in this case. So that would give us 8 times 2x plus 3 cubed. So now if we wanted to do the second derivative, Bring the 3 down would give us 24. 2x plus 3 squared, times it by 2 again. So you can see we'd have 48. And we could keep going just like we did with the last one, right? The basic chain rules don't really change very much. You just keep bringing your number down and following those chains. So let's do another one where we actually try to plug in a value. So here's our original equation. So our first derivative would be, using power rule, we'd have 48x cubed minus 6x. Do our second derivative, and we would get 144x squared minus 6. So the only thing that's different with this now is we're going to be plugging in a value. So remember, if I was to plug an x of -2 into the original equation, that's going to give us the y coordinate, right? Because on that graph, we would say on this graph, when x is -2, our y value is whatever. If I plug the -2 into our first derivative, that'll tell us what the slope is at that -2. So that would be a slope of whatever that answer would be. If we plug -2 into our second derivative, which is what this question's asking, you can see we get a different answer. And in this case, it's quite a big number. Let me just calculate it here quick. We get -2 squared times 144. Take away 6 gives us 570. So if the first one gives us the y coordinate, the second one would give us the slope. My question is, what does this 570 represent? So if the first derivative is slope, the second derivative now would be like the rate of change of the slope, or the slope of the slope, which graphically doesn't really make that much sense. It doesn't really mean anything. If we approach this from a physics perspective, it might tend to make a little bit more sense. So let's do that. And like I said earlier, we're going to do more of these applications later, which will probably make a little bit more sense. But for now, I think this is a good way to think of these things. So if our original equation, instead of it being just y equals whatever x, if we think of it as distance equals something time, this might make a little bit more sense. So if we do our first derivative of this equation, so let's just do it up here. So our first derivative would be -9.8t plus 8. If we did our second derivative, that would just give us -9.8. So from a physics perspective, this actually means something now. So if our first derivative, our first equation is just our distance time equation, if we now find the slope, you might remember from physics that the slope on a distance time graph gives us our velocity. So if we plug in our 1 value into this equation, so we'd have -9.8 times 1 plus 8, that would give us -1.8. So what we actually solved for is the speed. So at that location on the graph, we'd have a speed of -1.8 meters per second, or whatever our units are. So first derivative in terms of physics would be our speed. Our second derivative is the acceleration, because the rate of change of speed is telling us how fast we're speeding up or slowing down. And in this case, there is no t value, so this answer would just be -9.8. And you guys should know from physics, that is just basically our acceleration of gravity. So from an application perspective, sometimes derivatives don't really make sense for certain things, other times it will. Like in this case, our first derivative is speed, second derivative is acceleration, third derivative wouldn't make sense at all. Like there's really nothing that we usually do beyond acceleration. In university, I think they call it jerk. So there is a third one, and it just sort of tells you how fast your accelerating is changing. So I think the reason they call it a jerk is your body would kind of jerk around in a car if you speed up, slow down, hit the brakes or whatever. So it would basically be the speed of the acceleration, which, like I said, in most cases doesn't really mean anything. So some applications, first and second derivatives are perfectly fine. Others, maybe just the first derivative. Maybe others, the third and fourth would make sense, but it's not always going to be the case. So let's look at another second derivative scenario, but we're going to start with something a little bit harder. So far we've done power rule. We did one example of chain rule. Once we get into product and quotients, things start to get a little bit more difficult. So let's leave this one as a quotient, and let's do our f divided by g notation. So if f is 2x squared, our derivative of that would be 4x. If our bottom is the g, The derivative of that is 3, so that's pretty good. But now when we do our quotient rule, let's follow those steps. So our first derivative should be those two multiplied together first. So let's multiply those two, take away the other two, all over the bottom squared. Okay, so that's a little messy, so let's clean up the top a little bit. So the top would simplify to 12x squared minus 4x, take away 6x squared, all over the bottom still. And let's even simplify that top to be 6x squared minus 4x. We'll just put the 12, take away 6 together. And our bottom would stay the same again. And we're done. So that would be our first derivative for this question. We don't want to simplify it any further. If we factor the top, we're going to turn it into a product quotient chain combo, which isn't good. So for this one, we can see it's pretty messy to go from first to second, or from the original to the first, but it even kind of gets worse when we go to our second. So for our second derivative, if we take this equation, let me rewrite it, but let's write it as a product chain combo. So we'd go 6x squared minus 4x, and we're going to times that by 3x minus 1 to the negative 2, right? Bring that bottom up. Now you can see we're running into another issue. We've got our FG thing again as a product rule, but one of them is chain rule. So this is where we get into those combo questions where it works, it's just that we have to do common factoring. So let's write our FG stuff first before we get into the product rule. So let's call F that first term. So that derivative would be 12x minus 4. And G is our second term. So that derivative we have to use the chain rule. So it'd be negative 2 times 3x minus 1 to the negative 3. And we'd have to times it by 3. So let's simplify that to negative 6 times the brackets. Okay, so now we're ready to do our product rule. So let's do our second derivative, which would be those two multiplied again. So let's write it as 12x minus 4 times 3x minus 1 to the negative 2 plus the other 2, but we have a negative in there, so it'll turn it to subtraction. So we have negative 6 times our 6x squared minus 4x times the bottom brackets. That was negative 3. Okay, so there's our product rule of that first derivative. So now we just have to simplify it, and we're right back to when we did the chain rule combos. You want to pull out your common factor. So in this case, we could take out a 2 out of the beginning or something like that. Let's just leave it. I think it'll simplify quite nicely anyway. So let's just take out of the 3x minus 1s, let's take out the smallest power. So you'd have 3x minus 1 to the negative 3, and then the leftover, we'd have our 12x minus 4, and we'd have an extra 3x minus 1. And then for the second part, we'd have just the stuff at the beginning. And then the 3x minus 1s would cancel. Okay, so all we need to do is let's simplify those square brackets. So let's FOIL it out here. We'd have 36x squared when we do those two, minus 12x, minus 12x again, plus 4. And then let's do this foiling. So we would get minus 36x squared plus 24x. And it nicely cancels things. We have 36x squared minus 36x squared minus 12, and minus 12 is 24, which would cancel with the 24. So all we get left over is the 4. So often with these kind of questions, this kind of thing will happen where we get quite a nice simplification. So after all is said and done, all we have left over is 4 times our 3x minus 1 to the negative 3. So that would be our second derivative answer. The reason why we want to simplify these things is now if we had to do our third derivative, it's actually really easy. We bring the negative 3 down, so we'd have negative 12. We'd drop our power to negative 4, and we would have to times by the derivative of the inside, which is 3. So it'd be negative 36 to the brackets of -4. And then from there, it'd just be chain rule, chain rule, chain rule. It wouldn't really make any difference. So for this question, we did a little bit of work to do our first derivative, quite a bit more work to get the second, and then after that, once we simplify it, the third and fourth and so on would be quite easy. So I have one more question, and it's, can we combine everything that we've just done now together? So we've done implicit, we've done higher derivatives. What happens if I ask you to do a second derivative of an implicit equation? So the nice part is it works pretty good as well. So let's go back to the drawing board. Let's do our first derivative. So we're just going to leave it as an implicit equation. So our first derivative would be 8x plus 2y dy dx equals 0. So that's pretty simple. Let's bring the 8x to the other side, and we'll divide by 2. So I'll do this all in one step. Bring the 8x over would be minus 8x. Divide by 2y would be that. So our final first derivative should be just -4x over y. Or we could even write it as -4x y to the -1. So either of those would be fine. But if we're going to do our second derivative, I think it's going to be better to do the product. So what I would do is rewrite it as the -4x to the -1. Let's do our f as being the -4x and the g as being the y to the -1. So let's do that quickly. So if f is -4x, f prime would be -4. If g is y to the -1, g prime would be -y to the -2 times dy dx, and that's where the issue happens with this one. So the steps are still the same. We just got to be careful with implicit to make sure we don't forget that extra dy dx. So now when we go back to the product rule, our second derivative now is this cross multiplying. So we get -4y to the -1 plus the other two, which would give us positive 4x y to the -2 dy dx. And here's where we run into a bit of an issue with implicit. So we found our original derivative was dy dx. We're looking for our second derivative now, but we get an extra dy dx as part of our second derivative. So we don't stop here. We don't want to have two dy dx's. We can't cancel them out. They're totally different things. One of them is slope. The other one is like the slope of the slope, or think of it as being one is speed and the other one's acceleration. You can't combine those. So what we're going to do though is we're going to take our dy dx answer that we already calculated, and we're going to substitute that in to try to get rid of some of those extra terms. So our simplified answer would be d squared y over dx squared. Our first term stays the same, and our second term we're going to multiply by our first derivative answer, which was 4xy to the -1. So all we're going to do is try to simplify this a little bit. So we multiply those, we'd have -16, add our x's would be x squared, add the y's would be -3, and we could either stop there, or if we wanted to, we could common factor out a -4y to the -3, right? Always take out your smallest one. So that would give us y squared minus 16x squared. And we could stop at that. Oops, sorry, I messed up. Let me fix this a little bit. So first thing I messed up on is when we divide -4, we got y squared. We divide it from -16, that would give us +4. And that's it, yeah. So -16 divided by -4 would be +4. The x squared would stay. The y cubed cancels. So you can see that's a little bit of a nicer version, but there's actually one more little trick we can do, is that our simplified version, this y squared plus 4x, actually matches our original equation. So we can actually do another substitution, and everything that I've got in brackets there, you can see from the original equation, is equal to 4. So this simplifies actually quite nicely to just be -4y cubed times 4. So we could write that answer as -16y to the -3. So that would be probably the best way to write our second derivative. Or you could write it as -16 divided by y to the cubed. So what's weird is with these implicit second derivatives, often we get this substitution thing. We can substitute the dy dx in, and when we do that and simplify our common factors out, often we can substitute the original equation back in as well. So for this one, final answer, negative 16 over y cubed would be our second derivative. And now if we were to do our third derivative, that would be a lot simpler, right? Let me just write it over here. So if our second derivative is negative 16y to the negative 3, if we were to do our third, we would just have to do power rule on that. So that would give us 48y to the negative 4, but then we'd get another dy dx on there because of the y. So then we're going to have to go back and substitute again. So you can see, it's even though we're still substituting, it ends up being a little bit easier. We would have whatever 48 times 4 is, x y to the negative 5 would be our final answer for that one. The fourth derivative would then be tough again because we're back to a product rule situation. So you get the idea. A point I wanted to make is substitute your dy dx in, and then sometimes when we simplify it, we can resubstitute the original equation back in as well. And that's all for derivatives. We're going to move on to logs and trig in the next section. Still dealing with derivatives, still doing product rule, chain rule, all that. Just we're going to look at it from a trigonometry and a logarithm point of view. That's all.